Chapter 6, Sets. Okay, we've all seen sets before. You probably have some familiarity with them already, but let's review a couple of things here and we'll develop some notation as we go along. First of all, set is just any collection of things. There's a set right there, and we'll give it a name. And a couple of things to note about sets. First of all, these are called the elements of the set. And when we're specifying a set, the order of these things doesn't matter. So if I were to come over here and say A is equal to okay, over here I've changed the position of cat and dog. These two sets are exactly the same thing. The order in which these elements appear inside these brackets, okay, and we have to be very careful here. These are these kind of brackets because we're going to be using other brackets to represent other things. The order in here doesn't matter. The other thing that we can say about sets is that it doesn't matter how many times you repeat elements within the set. So if I were to come over here and write this set over here, okay, we notice that in this set we've repeated dog twice, okay? But we don't care about how many times things repeat in a set, and by convention what we do is we list elements of the set only once. But all three of these sets are specifying exactly the same thing. Now a little bit of notation here. We talk about membership in a set. Membership. And in the example that we are given here, we would say that dog is an element of the set A. Okay, that little Greek epsilon, that little e there, if you will, that means is contained or a member. We could come along and we could say something like the following. We could say that lion is not an element of A, and we indicate that by drawing a line through that. Okay, not a member. Like such. Now, for very small sets, like this one right here, it's very easy just to actually explicitly list the elements of the set. Sometimes that's not so easy to do. Sometimes the set may be rather large, or we may not be able to expressly give the elements of the set. But we have another notation that we can use in set theory. It's sometimes referred to as set builder notation. And I might come along and say something like the following. I might say that the set B is equal to okay, So the way that we would read this is we would say that B is equal to the set of all X such that this vertical line here, we say that such that, and notice what follows the such that. This looks very much like a predicate that we had back in chapter 3. And in essence, you could think of it that way. As I'm making this video, I don't know who the students are in this class, but what I've done over here is I've actually specified the set of all the students in this class. So this is referred to sometimes as set builder notation, and we will be using this one a lot. Let's talk about some famous sets. The book has actually been using these already, but it might be nice to formalize them right here. One famous set is what's called the natural numbers. And very frequently in mathematics, you'll see that written. It's called n, and sometimes what people do is they make it a double line over there on the beginning. And the natural numbers, 1, 2, 3, and it goes on forever and ever like that. Okay, so notice that it starts at the number 1. Another famous set is called the integers. And again, this frequently is denoted with a Z. And again, very frequently in books, they make this double over there. The reason why they use the letter Z, it comes from the German word Zahlen. Zahlen means to count. And this set looks like the following. So, whereas we notice the natural numbers, there is a smallest natural number, 1, and it heads up here to infinity. When we talk about the integers, it actually goes towards minus infinity and it goes towards positive infinity. Another set we should know about are called the rational numbers. And here we're going to have to use our set builder notation. And I'm going to say that's equal to the set of all A divided by B such that A and B are elements of the integers and B doesn't equal 0. So the rational numbers include things like 1/2, or minus 37 over 16, or 2 1/8. Now you're going, wait a second, 2 1/8 isn't an A divided by B, but we note that 2 1/8 is actually equal to 17 over 8, and that is of the form A over B. And lots of other numbers. Okay, so those are called the rational numbers. Oh, by the way, this is sometimes denoted, very frequently denoted by the letter Q. Q stands for quotient. Okay, we have the real numbers. And that's denoted by this funny looking R. And it's really very hard to describe this one as easily as we've described these previous 3. But the real numbers you could think of, you've all seen the real number line. Okay, and it consists of all the points. Notice we're going over here to positive infinity, and over here we're going to negative infinity. And it's all the points on this line. So there are a couple of things to notice here. First of all, notice that the natural numbers, all natural numbers are integers. Notice that all integers are rational numbers, and notice that all rational numbers are real numbers. So one of the questions you might be asking, now, I'm not so sure that are there any real numbers that aren't rational numbers? In other words, are there any points on this line that can't be expressed as an integer divided by another integer? And the answer is yes, there are quite a few of them. Examples of that might be something like the square root of 2, or another one might be pi. Maybe another number, maybe you're familiar with this number or not. E, square root of 3. There are a whole lot of numbers, okay, in here that are not in here. And in fact, these numbers have a special name. These are called the irrational numbers. So if we were looking for a definition of irrational numbers, we could say that irrational numbers are real numbers that can't be expressed as an integer divided by another integer. And we will show later on, we'll pick a couple of these out. Square root of 2 is a pretty easy one. We'll show that this is irrational, okay? In other words, we will show that radical 2 doesn't equal a over b for any a and b that are integers. It's a very interesting proof. Given two sets A and B, we say that A is a subset of B, and we write that this way. If and only if x is an element of A, then x is an element of B. Okay, and we would say that A is not a subset of B. Just put a line through it like that. If and only if there exists in X such that okay, what do you think that would be? Well, I think that would mean if there exists an X such that X is contained in A and X is not contained in B. Okay, now this definition over here, this may include the fact it's possible that A could equal B. Now, to show to show that two sets are equal, we actually have to show two things. We'd have to show that A is a subset of B and B is a subset of A. If both of these conditions are true, then we would say that they're equal. On the other hand, we could write something like the following. We just write it this way, and we would read this: A is a proper subset of B, and that's if and only if there exists an X such that X is contained in B and X is not contained in A. Okay, let's consider a couple of things that we already know. We know that the natural numbers are a subset of the integers. Okay, but we know that there are integers that are not natural numbers. Can you think of one? Sure. What about -3? Okay, -3 is not a natural number. So we can actually conclude from this that the natural numbers are actually a proper subset of the integers. Okay, just some notational things that we need to talk about. Let us consider this set right over here, A. And notice that A has 3 elements in it, but notice 2 of them are sets, and that's perfectly permissible, okay? So I want to note a couple of things over here. Certainly the integer 1 is an element of the set. This is a true statement. And I come over here and the set 2, 3 is an element of A. That is true. And I also note here that the set 4 is an element of A. Now, these are all true statements, but I want you to note that the integer 4 is not an element of A. The set containing the integer 4 is an element of A. So this is a very important distinction for you all to understand, okay? Now, we've spoken a little bit before about subsets, and we're going to speak about them some more. So I want you to note over here that the set containing the element 1 is a subset of A. In other words, remember what it means to be a subset. It means that if X is in this, then X is in that. Well, if X is in this, the only thing it can be is the integer 1, and X is in A. It's right over there, okay? Likewise, we note that the set consisting of the set 2, 3 is a subset of A, okay? Again, we notice that the set containing the elements 2 and 3, that is an element of A, so this is a subset of A. Now, we're going to be talking about this is very important. We're going to be talking about this thing called the null set. There's a very strange set that exists out there in set theory, and it's the null set. And it's the set that contains nothing. There is no element of this set. And we have 2 ways of denoting it. One is just we use the braces here to indicate a set, but we don't put anything inside. The other way to do it is to draw a 0 with a line through it. I think we're going to try and stick to this notation here, but sometimes I may forget, okay? So a very important fact is that the null set is a subset of any non-empty set. Now, let's think about what that's saying. We're saying over here that the empty set is a subset of A if and only if. And then we have to come over here. The definition of being a subset means that if an element is in this set, then it's in that set. So we're rewriting it over here. If X is an element of this empty set, then that would imply that X is an element of A. The question is this a true implication? Well, here's the weird part. X is an element of the empty set. Okay, now nothing is an element of the empty set, which means that this statement over here is false for any X that we have. But remember, when it comes to implications, implications are true whenever the hypothesis is false. So this is a true statement. This statement over here is true. And if this statement over here is true, that means that this statement over here is true. So the null set is a subset of any set. Let's consider a couple of examples out of your book. Now, one of them comes over here and it says, let's define a set A. And let's A be a set that looks like the following. It's the set of all integers m such that m is equal to 6r plus 12 for some r in z. Now, before we go on, and your book doesn't do this, but I would like to, that's a wonderful expression there, but I want to know what A looks like. So what I can do is I can come over here, and I'm going to start picking R's contained in Z. I'm going to pick integers, I'm going to stick them into this expression, and I'm going to see what happens. For example, if R is 0, then M is equal to 12. So I see that 12 is an element of this set. And if R is 1, then I come over here and I calculate this, and it says, oh, well, 18 is in there. And if R is 2, well, 2 times 6 is 12, plus 12 is 24. And I think I'm starting to see a little bit of a pattern here, 12, 18, 24, 30, 36. And it looks like it goes on for infinity that way. What happens if I go to the other way? So I've tried R is equal to 0. What happens if R is equal to minus 1? If it's minus 1, it's going to be minus 6 plus 12. Well, that's going to be 6. And if R is minus 2, this looks like it's going to be 0. And I think I'm starting to see a pattern here as well. So this up here looks like it's describing this set right over here. Okay, now the other set that they ask us here is they say let B equal the set of all n contained in Z such that n equals 3s for some s contained in Z. And again, I'm a little uncomfortable with this. What I want to do is I want to start figuring out what the set B looks like. Well, for any s contained in Z, well, if s is 0, 3 times 0 is 0. And if s is 1, then 3 times 1 is 3. And if s is 2, it looks like I get a 6. And then 9. It looks like it goes on that way. And I can start sticking in some negative integers here. If I stick in a minus 1, I get minus 3. If I stick in a minus 2, I get a minus 6. And I think I'm seeing a pattern here. So that's what B looks like. Now what the problem in the book is asking us to do is it's asking us to prove A is a subset of B. And remember what that means. That means that we have to show that for any x contained in A, okay, we need to show any x that is contained in A is contained in B. Now, first of all, just looking at these sets, I think you can see that that's a true statement. Okay, for example, I come over here and I see a 6, and I go, oh yeah, well that's in there. And over here I see a 12. Well, that would be the next number right over here. So I think you can see that this is true, but just this is a proof by picture, which really is not a formal mathematical proof. What we need to show is we need to show that any x in A is contained in B. So, okay, suppose x is in A. If x is in A, then x is equal to, and I come right back to the definition over here, it's equal to 6 times some y plus 12 for y an integer. Okay? Now notice I changed the r to a y. That's fine. We're indicating that it is an integer, just like this r is an integer. Okay, so if I have this over here, then I say, but six y plus 12 is equal to 3 times 2y plus 6. Okay, that's simple mathematics. Okay. And then I say something like the following. If y is an integer, then 2y plus 6 is an integer as well. Right? In other words, if I have an integer and I multiply it by 2, I still have an integer. And then if I add 6 to it, I still have an integer. Okay? So what I've done here is I have now shown that if x is equal to 6 times y plus 12, I can rewrite 6y plus 12 as 3 times 2y plus 6. But 2y plus 6 is an integer. And notice here, I have shown that any number that's contained in A can be rewritten as 3 times some other integer. Okay, therefore, okay, x is contained in B. And I'll put these there to indicate that the proof is done. So what have I shown here? I have shown that A is a subset of B.
Will it blend? That is the question. Are you having trouble deciding which new phone to get? Nah, neither are we. But we have 2 phones here, and some people are telling me they're having a hard time making up their mind. So I am going to help them out. Are we ready? Lumia 929? Nobody wants that. Here, the Galaxy Note 3. And over here, Seems like this larger size doesn't want to come out. Ah, the iPhone 6 Plus. I think I'll press the Newton button. And over here, I think I'll press the Who's Copying Who button. Oh, phablet smoke. Oh, don't breathe this. Where's the plus?
Oftentimes, when we're talking about sets, it's convenient to talk about what are called Venn diagrams. Okay, and those are just pictures of what's going on with these sets. So what I want to do is I want to return to an example we used a long time ago when we were talking about logic, and I want to let A be equal to the set of all Namibians. And I'd like to let B be equal to the set of all X such that X is tall. And for the moment, why don't we just restrict ourselves to people? Okay, now we come over here, a Venn diagram says do the following. We'll draw a square, and this square over here, this is the universe. And somewhere inside of here, this is the set A. So inside the universe here, we have the set of all the Namibians. And maybe what we have over here, maybe I can get clever here and try using a different color. Let's see if that's going to work. I come over here. Oh, look at that. Here's the set B. And B represents the set of all tall people. Now, notice what we have over here. Here's a very interesting area. Okay, notice that if I have someone in there, if X is in that crossed area there, then that means that X is Namibian, and X is tall. Okay, now we have a name for that, and the key thing to notice here is the word and. In set theory, this is what's called intersection, and what we have here is A intersection B. And we would say that X is contained in A intersection B if and only if X is contained in A and X is contained in B. Okay, right over there. Okay, now it could certainly be the case that this is an empty set. Suppose I would have X is Namibian, or A is the set of all X's that X is Namibian, B is the set of all X such that X is tall, and maybe we would have over here that C is equal to the set of all X such that X is Kenyan. Now it could be the case that here is the set C, so again, we see that there are some tall Kenyans, but we would go, if we were to look at A intersection B, or I'm sorry, A intersection C, this is the null set. Okay, and what that's asserting is that you can't be both Namibian and Kenyan. Okay, now maybe in reality you can, I'm not sure, but the way that we've drawn it over here, you can't. Okay, so this represents intersection, and in a moment we're going to introduce some of the other drawings. All right, let's draw another picture here. I'm going to stick with red just for variety. So here's our universe. So why don't we let A, I'm going to be very informal here, Namibians. Why don't we let B equal Kenyans? Why don't we let C equal basketball players? So let's make pretend that that is A. Let's make pretend that is B. And let's come over here and do something like this. Why don't we make that C? Okay. Now, as we noted in the last slide, we noticed that A intersection B is equal to the empty set. Intersection would require points to be in both A and B. But there's something else that's called the union. Okay, and I'm going to say here union. And X is contained in A union B if and only if X is contained in A or X is contained in B. So notice we have the word or here. So if I wanted to draw a picture of what A union B looked like, let's have fun here and pick even a different color. Okay, so it's either in A or B, so it's going to be anything in here. That's A. And that's B over there. So I'm going to say it's this. Okay, and notice that A and B don't even have anything in common here. Okay, that's fine. Okay, but we can see that this is a non-empty set. Now, for example, if I wanted to talk about, and again, let's pick another color. I'm not sure why I can't do that now. There we go. So let's go back to our red. if I wanted to talk about A union C, okay, now that's going to be, let's pick out a different color so that we can recognize that. How about blue? There we go. Okay, so if X is in A union C, it's either in here or it's in here. So it's going to be, it could be here. And it looks like that. Okay. One other definition here, the complement. And this is the complement. And we would say that X is contained in A complement if and only if X is not contained in A. Everybody okay with that? So maybe we can draw a picture of that. Color, please. Why don't we pick gray? Okay. So if I come over here and we can see that this is A over here, A complement is going to be all of this. Okay, so notice that A complement includes parts of B and C over here, okay, but nothing inside of A. So that's A complement right over there. Okay, we want to introduce the notion of what a partition is. Let's change our color. We'll go back to black. Okay, black. So what we want to suppose here is that we have a set A. We'll make this pretty simple right now. 1, 2, 3, 4, 5. And what I want to do over here is I want to do the following. I'm going to have a set here P1. And I'm going to let that be 1. And have P2 is equal to 2 and 5. And I want to have P3 is equal to 3 and 4. Okay? Now I want you to notice a couple of things over here. I want you to notice that P1 intersection P2 is equal to the empty set. And that P1 intersection P3 is also equal to the empty set. And I want you to note that P2 intersection P3 is equal to the empty set. So basically I'm going to make a general statement here, and I am going to say that PI intersection PJ is equal to the empty set for IJ equal 1, 2, 3, and I doesn't equal J. In other words, what I'm claiming here is that this statement right here is saying exactly the same thing as this statement right here. Okay, and I hope that that's clear. All right. Now, we have a definition to make here. Whenever this is true, we say that Pi and Pj are mutually disjoint. Okay? In other words, the intersection of any two of these is always empty. And the other thing that I want you to note here is that P1 union P2 union P3 is equal to A. Okay, so this is a lot to think about here. What we've done is we have taken A and we've broken it up. In this situation, we broke it up into three pieces. Each one of the three pieces are mutually disjoint, and the union of the three pieces gets us back to A. This is what's called a partition. This is called a partition of A. And we'll even say it's a partition of A by P equals P1, comma, P2, comma, P3. Now please note that for a particular set like this, there are many partitions. For example, we could have had 5 different subsets. One could have had 1, one could have had 2, one could have had 3, one could have had 4, one could have had 5. Each one of those subsets is mutually disjoint, okay? And the union of them all give you back A, okay? So this is what's called a partition, and we will be using partitions. Okay, we need to talk about what are called power sets. Okay, and a little notation here. If A is a set, then we have a script P. P of A is the power set. So the question is what is a power set? The power set is the set of all subsets. So let's just do something very easy. If A is equal to the set 1, 2, suppose I wanted to list all the subsets of that. Well, 1, 2 is certainly a subset of A. And then 1 is a subset of A. And then 2 is a subset of A. And then remember, we talked about how the null set is a subset of every set. So these are the subsets of A. And there's a very important property to note here, and we need to talk about this right now. If I have a set A, this represents the number of elements in A. So in this example right here, we would have A is equal to 2. Sometimes you'll hear people refer to this as the order of the set. or the magnitude of the set. Okay, and a very important property here, you can see that in this case, A had 2 elements in it. How big is the power set? The power set is 4. Now remember, the power set is the set of all subsets. So if I were to really, I would have to say that P of A is equal to 1, 2, 1, 2, and the empty set. And a very important theorem of mathematics says the following, that the size of the power set is equal to 2 to the size of the set. This is very important right here. So think about what that says. That says that if A, or let's come over here, if I have B is equal to 1, 2, 3, then the size of the power set of B is equal to 2 to the third, which is 8. Okay, I have a set over here with 3 elements in it. Its power set is going to have 8 elements in it. And I leave it as a homework exercise for you to list all 8 of the subsets of B. The last issue to talk about in section 6.1 is this notion of what's called a Cartesian product. And what that means is the following. Suppose I have a set A, which is made up of A, B, and C. And suppose I have a set B over here, which is made up of 1, 2. Okay, so I have 2 different sets. Now, what I can do is I can form a Cartesian product over that. And what that means is I'm going to come over here. Now notice I'm using different brackets here. These are rounded brackets. And what goes over here, this is from A. And what goes over here, this is from B. So I can actually list all of the Cartesian products over here. I could get A1, and I could get A2, and I could get B1, B2, and I could get C1, and I could get C2. And the thing that is very important here is remember when we talked about sets and we talked about 1, 2, and we said, well, gee, that's really equal to 2, 1. When you use these kind of curly braces and we're talking about sets, the order of the elements doesn't matter. But in Cartesian products, the order does matter. And what we've specified over here is that the first entry over here has to be from A and the second one has to be from B. And I think that you can see that if I were to be considering a Cartesian product of 2 sets, the number of elements in the Cartesian product is just going to be the number of elements from here times the number of elements from here. Now I could certainly extend this beyond 2 coordinates. I could have 3. I could come over here and this could be from A. This could be from B, and this could be from some other set. Maybe C is equal to happy face. and sad face. So that an element from here might look something like this. It might be B2 happy face. Okay, the order is important. If I wanted to know how many of these are there, well, there are 3 that could come from here, there were 2 that could come from here, and there were 2 that could come from here, so that would be 3 times 2 times 2. There would be 12 different possibilities for this Cartesian product. Okay, we will return to this again later.